This lecture covers sections 6.2 through 6.2.3. At the end of today's lecture, you should be able to understand the relationship between stress and strain for ductile materials and identify key properties of these materials, such as the yield and ultimate stresses, as well as the linear elastic region on the stress-strain diagram for both low-carbon steels and aluminum alloys. You should also be able to understand the relationship between shear stress and shear strain and how they are related via the shear modulus, as well as understand the formulation of Poisson's ratio and how it relates the modulus of elasticity to the shear modulus. The motivation for this lecture stems from Lecture 16, where we learned that the stress developed within a member depends on both the applied load and the cross-sectional area of the member. Members with differing geometries experiencing the same load experience different stresses, which makes it difficult to quantify the material's performance. To more easily analyze materials, we can remove the geometric dependence from the expression. Let's consider a bar with a constant cross-sectional area A and a length L. When an axial load P is applied to the bar will deform some distance delta. If we plot the applied force versus the deformation, we have the following curve. It starts out linear, is followed by a dip, which is then followed by a nonlinearity. This tells us about the behavior of the material as a function of the applied load, but what happens if we change the geometry of the bar? For instance, if we double the cross-sectional area, we'd have to apply 2p to elicit the same deformation. This makes sense theoretically, and we can prove this experimentally. In both cases, the bar with a cross-sectional area A and applied load P and the bar with an area 2A and applied 2P, they'd be experiencing the same normal stress, where sigma is equal to R per A. In both cases, the deformation delta is going to be the same, and the initial length L is the same, so the ratio of delta per L is also the same. To remove some of the geometrical dependence, we have to introduce the concept of strain, which is defined as the deformation per length. The average axial strain, epsilon, is defined as delta per L. Let's consider a bar that's 0.6 meters long and has a uniform cross-sectional area. This bar experiences a deformation of 150 microns due to applied loading, and we want to determine the corresponding strain. Recall that strain is equal to the deformation per length, where we'd have 150 microns divided by the initial length of 0.6 meters. This gives a strain of 250 e to the minus 6 meters per meters, or 250 mu. Units of strain are dimensionless, but we're going to retain a dimension associated with it, meter per meter, centimeter per centimeter, inch per inch, etc. Or, what we can do is take the prefix that would denote the magnitude of the unit system and solely leave that.